Hi, I'm Ben-Yaakov. This presentation is entitled GaN Gallium Nitride Gate Injection Transistor or GIT driver. There is a disclaimer here that the devices shown in this presentation are for educational purposes only. No recommendation or endorsement is implied. Now, in power electronics, we are accustomed to the silicon MOSFET, and MOSFET meaning that the metal oxide field effect transistor, and the metal oxide is this layer here, which is actually insulating the gate from the channel. So the gate is insulated from the channel. This is, by the way, the source. This is the drain. Here is the gate. And therefore, there is no galvanic connection between the gate and the channel. So there is no DC current coming in or out. Now, during the switching, turn on and turn off, we do need to inject current. So these are actually high current pulses, but the net average is zero because there is a insulation here, no galvanic connection. Now the GIT transistor is different than the silicon MOSFET in that there is a galvanic connection between the gate and the channel. There is no insulation here. In fact, it looks like a diode between the gate and the channel, the source, you might say, in this case, and it is therefore conducting DC. It can conduct and should conduct, in fact, for proper operation. So the driver has to be designed such that it will take care of this DC component. And this is the subject matter of this presentation. Now here is a simplified equivalent circuit of the GIT transistor. It's by Infineon for the cool gun, as they call it, this family. And what we have here is the basic transistor itself, and then the parasitic capacitances. This is very similar to the silicon MOSFET, the gate to drain, gate to source, and the output capacitor. Here now we do have a diode. So this represents this conduction path between the gate and the source through this diode. This is the equivalent circuit. In fact, this is not a diode. It is more like a Zener diode, because when the voltage is negative, then if you pass a certain voltage, in particular transistor we're going to talk about, it is 10 volt. So if you pass the minus 10 volt, then current will start actually flowing, the DC current. So it's more like a Zener diode. And then in this model, they have put here the RDS1 and the parasitic inductance primarily due to the bonding. Now here is actually a Kelvin connection, and this is the source. So this is the drain, this is the source, and it's a Kelvin connection, the gate. And the main difference is this diode here, which is now passing DC current. If we look at the switching requirement of this GIT transistor, here it is, as compared to the silicon MOSFET, there is not much difference in shape, but rather in values. That is, we see here the Miller plateau, like in here, and then this is again will be the charge to the gate, and this will be the voltage gate to source. This is a voltage gate to source, and we see that in the case of the GIT of this transistor, the amount of charge is smaller, 5 nanocoulomb up to this point, while here it's 50. And this is because, of course, that the capacitances, the parasitic capacitance of this device are much smaller. This is the whole point, which makes it faster. So the charge is smaller. And also the threshold typically will be lower. It'll be like 2.5 volt, rather than the, say, 6 volt at many silicon MOSFET show, although there are some, of course, that with lower threshold. So at any rate, the general shape is very similar, which means that the drive requirements are not that different. I mean, they are different maybe in the magnitude, but not in the nature of the requirement of a current pulse during the turn on and turn off. And here is the key parameters of this device. These are not much different than the silicon MOSFET. The maximum voltage of this particular device that I'm now looking at, and for which I'll sort of match the driver, is in this particular case the maximum voltage is 650 volt, and the RDS1 is 30 milliamps, so it's a hefty transistor. And indeed, the pulse current can go up to 120 amp. So it's a fairly large power transistor, 650 volt. So it'd be useful, say, for 400 volt bus and a little bit higher than that. So this is very similar to parameters that you'll get with the silicon MOSFET. But here are some parameters that are really unique to the GIT. We see here the gate current continues, and this is 46 milliamp, and now this is DC current to the gate. Well, obviously, you don't have it in the silicon MOSFET. However, during the transition, we do need high current in order to turn the transistor fast on and off to supply the charge to the gate. So therefore, we need high current pulses, and indeed, we can go up to 4.6 minus 4.6 to 4.6 amp during this transition. So this is just for the switching part, while the DC is limited to 46 milliamp. And then we have the maximum negative voltage to the gate, which is minus 10, and in the pulse could be up to minus 25. So these parameters are unique to the GIT. Now we have here the input characteristic of the gate, which is basically the diode, because we have conduction here, we have current here, so this is the part of the diode. So this is the forward. As I've said, we actually are dealing here with the Zener diode, so this is the forward. We see that the threshold is about 2.5 volt, at which the current starts to rise. And then this is the reverse part, minus 10 up to minus 10 volt, we have practically no current, and then we have a current starting up, so one has to be careful not to penetrate this region in continuous operation. For a pulse, we have seen that we can go up to 25 for a very short period of time. And then we have here the output characteristic, very similar to silicon MOSFET, except that here they are given here, or the parameter is the gate current rather than the gate voltage, which is given for the silicon MOSFET. Well, I don't know if this is really the correct parameters. It would seem to me that even here, the voltage is controlling the conduction of the channel, but nonetheless, there is a relationship between, of course, the voltage and the current through the characteristic of the diode. So here we have the current of the drain, the voltage drain to source, and the parameters again is the current. Now, as we know, this slope here is the RDS on. So now, if you like to go to a high current, then we need a fairly high or relatively high gate current. And we see that something like 6 or 15 milliamp will give us RDS on up to high current. So this probably will be the value that we would like to have. Now this is the same thing, except for this is 425 degrees. What is important for power electronics is, of course, the RDS on. So here we have this kind of strange plot here. This is the drain current. This is the RDS on. And here are, again, the injected gate currents. And now, if we like to have the RDS on, say, no more than 44 milliohm, and then we like to work, say, up to 60 amp, for example, then it turns out that we need for the on time, about 15 milliamp. Okay, so this is one point that we have to take into account. Now, this 15 milliamp can now be linked to the gate voltage through the characteristic of the diode. So 15 milliamp for a temperature in between 25 and 125 is about 3.25 volt. So to sum up, for the DC condition, we understand that during the on time, the current to the gate should be about 15 milliamp, and at that point, the voltage will be 3.25 volt at the gate to source. Summing all this up, we understand that we need a current profile for the gate that looks something like that. We need a high peak current during the turn on transition, and then we need some DC current through the on time, and then we need some negative peak current during the turn off transition. Okay, so the driver has to provide this shape. As far as the height of the peak, it's really like in the case of the silicon MOSFET. We start with the amount of charge that we need, and then we decide on the rise or fall time. Here I'm taking the fall time, and then the charge over the transition. The full time is actually the current that you need in order to pump into the gate. So this will be this current here, assuming it's about constant. Okay, that's just an estimation. So this is what we really need. So there are a number of ways you can produce this type of a profile. This is the simplest way probably. And what we have here is a regular driver. And then we have a number of resistors which provide different paths for the different region of operation. That is, for the DC, we have this resistor. Okay, so this is providing the DC path. For the turn on transition, we have this path. This resistor is smaller than this one. And then we have here a capacitor. So when we have here a step, then we'll have this step propagating and causing a current through this branch here directly to the gate. And then we have another resistor, which is of low resistance, which will be used for the turn off of the gate. And this when S2 is on and S1 is off. A little more sophisticated approach would be to use a driver that has two outputs rather than a single output of the half-bridge driver. So we have the switch of the upper transistor and the switch of the lower transistor. And what is really happening here is that when this switch is on, turn on, we have this current going through this transition, going through this path here into the gate. When it is in the steady state, we have this path here. When this is turned on, of course, this will be off. Then we have this transition here. And then during the off time, we have the galvanic connection here between the gate and ground. Now, this is then the expected profile, as I've shown earlier, and the expected voltage at the gate will be something of this nature. This is during the on time. Now, during the off time, we have here in sort of an overshoot and then a exponential decay. I'll talk about it in a minute. Let's go now over the different mode of operation of this switch. And I'm starting with the off state, that we have this switch or this MOSFET, say, on, and therefore we have here a connection through these resistors of the gate to ground. And then we turn on the upper transistor. This will be, of course, off. And we have this transition here. Then we have the current going to the Miller capacitor through the gate to source capacitor. And of course, part of it also goes to the diode. Then we come to the steady state or the on time. And then we are providing the required current to the diode via this resistor, which is the limiting current resistor. And then we have this transition back. When this transistor is on, this of course will be off. And then you see this capacitor is now already charged due to the current that was passing this way. So it is charged here. And therefore, during this time, we actually have a negative voltage imposed on the gate, added, of course, to the voltages according to this network. So this explains this jump here. This is the added voltage due to the voltage across the capacitor. And then it decays. It decays because during this off time, there is a path here for this capacitor to discharge exponentially. So this is why the voltage, the negative voltage, is actually decaying and becoming more positive. To get a better look at the pulses and currents of this driver, I've set up a simple LTspice schematic. Now, unfortunately, I could not find a good model of a GIT. I got a number of models, but none of them actually worked properly. There have been conversion problems. Some of them will not run. So what I did here is the following. I've sort of emulated or sort of mimicked the behavior of the transistor itself as a capacitor. However, to take into account this current of the diode, I've here used the current dependent source to emulate a diode. So this is sort of a poor boy's equivalent circuit of a GIT transistor, which also has the input diode in it. Now the diode is emulated by a dependent current source. This current source is defined as the current as a function of the voltage across it and the values of the table taken off the datasheet. So this sort of emulates the diode, and the driver itself includes here a square wave excitation. And then rather than having two outputs, I've put two diodes, one for sourcing and one for sinking. And here is the network of this driver. The table is based on the datasheet diode characteristic, that is the voltage of VGS and the current IGS. This is actually the diode. So by taking these points, the pairs of voltage and current, I've created this table, both for the forward part, and as I've said, this is a Zener diode, so we have also the reverse part. And here is a run to test this table. We see here, this is 0 volt. This is the forward part. We see here the current of the diode, and this is the backward or the reverse part. And we see that it's starting to conduct at about minus 10 volt. Here it is. This is this part here. And zooming in for the forward part, we see that the matching is pretty good. This is the simulation, and this is the actual datasheet information. We see there's about 3.25. It's about 15 milliamp. And it's about the same thing here. This is, of course, not exact and was done just for the purpose of demonstration. And here is the simulation of the driver. What we see here is the on period. We see the gate voltage, and then we see here the negative part that we discussed here, which is about minus 9 volt or something like that. It's in the safe region. We see here the current of the transistor. This emulates the actual input to the transistor itself, that is to the capacitances of gate to source and gate to drain. We see here about 2 amp and then minus maybe 5 amp, the hefty pulses. And here is the current of the diode. Here, due to the peak here of the gate voltage, there is an increase here. But then we have, during the on time, this value here. Now zooming in, we see that during the on time, the voltage of the gate is about, 3.7 maybe. And then the current of the diode is about 16 or 17 milliamp. This is just about the values that I've sort of discussed earlier. Aside from the configuration that I've shown for the driver, there have been a number of other suggestions for other type of a driver, other circuitry, and here's one of them. This is taken from a patent or patent application by this group here, and it is very similar to the simple driver that I've shown earlier, except that it has here a Zener diode, which has the advantage of clamping the capacitor voltage to a certain level so that the negative voltage of the gain of the gate will not go too low. Also, it might help at the very beginning of the on transition to get a higher current. So this is just one example. As a matter of fact, Infineon is suggesting a very sophisticated configuration, which is based on 4 switches. Okay, so they can sell a lot of drivers. It works similar to the configuration that I've explained. However, it has some improvements. So what are the conclusions here? First of all, that unlike the silicon MOSFET, the GIT gate carries a DC current. As a result, the GIT driver needs to provide high current at the switching instances on one hand, while limiting the DC current in between, so not to exceed the limit of the gate current. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it'll be useful to you in the future. Thank you very much.